Heard the word derivative. You've heard it, okay? A lot of people, when they think of calculus, think of the word derivative. So what does that tell you about how important it is? Pretty darn important. Okay? We are going to talk about some synonyms here pretty soon of the word derivative. I will expect you to give those to me, maybe in like a quiz or a test setting. Okay? We are going to take we're going to take today to go over the formal definition, kind of some things that we can do with it. Tomorrow we'll talk about using the derivative. We'll talk about derivative graphs. And then next week we'll start to look at maybe some patterns in what we're doing. Okay? So the first thing I want you to remember is that a tangent line is a line that intersects the curve exactly at one point. Okay? You talked about tangents in geometry when you did your circle chapter, right? You have a line that's just touching the circle once. Okay? Same concept here for a function, or doesn't even have to be a function, for a graph. A tangent line intersects the curve at one point. And what do we know about a tangent line or any line? It has slope. Two ways we can describe a derivative. The first one is called instantaneous rate of change. It'll be on the next slide. Don't think you have to try to guess how to spell that. Okay, instantaneous rate of change. When you hear the word rate of change, what do you think? What? Slope. You think slope. Instantaneous. What is that describing?
At like a single point.
At a single point. At that very moment. Okay? The derivative can be described as instantaneous rate of change, which is essentially describing the slope of a tangent line at any given point. So I'm going to go through this slide. Go ahead and write down this right here, and I'm going to take you through this picture. Okay? Now, those of you who like to count my slides and you see that there's 30 of them, don't panic. Like 6 of the slides involve this one picture, but it's going to change as I talk about it, and it'll take like 30 seconds to get through 6 slides. Okay? Okay? What is this right here? Thank you. It is the slope equation. Difference in y's over difference in x's. Do you see it now? Do you see it? Okay, so this right here is describing the slope of that blue line. Right now it's a secant line. Why do I describe it as a secant line?
Because it intersects it twice.
Because it's intersecting it twice. Okay? So I'm going to take the limit as these two get closer together. Okay? Are you ready?
Should we draw that?
What?
Should we draw that?
That is up to you. Okay? Because this is what's going to happen. I want you to watch. You ready? Pencils down. Okay. As we take the limit, as x sub 1 approaches x sub 0, that means we are bringing those two x values closer and closer together. And we're doing so until they finally approach, boom, we have a tangent line. Okay, so when we took the limit of that slope of the secant line, we brought those two x values closer together until we approached what was now the tangent line. Okay, so this is what I need you to write down. Does that look familiar? Does that look familiar? Yes, you've done this before. Did you know that you've taken a derivative if you didn't know it? Now you do. Okay, this is the derivative. Go ahead and write it down and then I'm going to talk about it. It's essentially what I just went through, but it's formatted a little bit differently. Okay, so after you write it down, I will describe to you how it's the same as what we just went through. Sorry, my slippers are kind of. Okay. So what I have right here is still the slope of that secant line. Okay. F of x plus h, well, okay, delta x. Let's talk about delta x. Delta x is describing change in x. Okay, so instead of saying like x sub 0 and x sub 1, I'm just saying the change in x. So we start here at x and then we have a change in x. So when I say f of x plus the change in x minus f of x, that's still saying y minus y. So our new y minus the y where we started, okay, over delta x, change in x. That's essentially x minus x, okay? As delta x approaches 0, so as the change in x approaches 0. So essentially what we're doing, we're taking this secant line, and as we bring the two x values closer and closer together, that's what we do with our limit. We're bringing those closer together. We get the tangent line. So by taking the limit of the difference quotient, you are actually finding the slope of the tangent line for that graph. So you've written it down, but I want you to like circle it, make a big star, something. This is the definition of the derivative. And I need you to write this notation. Do you see this right here? This is f, and I'm going to call it prime of x. That is the notation for the derivative. When you have like that little tick mark, f prime of x, that means derivative. Okay? This is the definition of a derivative. And somewhere on your paper, in your notes, you need that a derivative is the slope of a tangent line and the instantaneous rate of change at any given point. When I say derivative, you're thinking of both of those things. If I say instantaneous rate of change, you're thinking of slope of a tangent line or a derivative. Okay? The derivative, slope of a tangent line, instantaneous rate of change, those three need to be grouped together in your mind. Okay? If you see one, you know it means the other. So luckily, you've actually had practice in taking the limit of the difference quotient. Okay. So really, the only thing that we're adding in today is what it means. Okay. So we're going to go through finding a derivative, and then we're going to talk about what it tells us. Okay. Are you ready? Okay. Please write down f of x. No, we're not ready. By the way, will band people be playing in the homecoming pep rally? Yes. So please raise your hand if you're going to be late to class tomorrow. Band and cheerleaders.
Because of court.
Yes, because you'll have to change. Is your outfit a surprise? That's probably my favorite part, is seeing how everybody dresses up.
I'm excited. They're pretty good. So.
Good. Okay, so I want you to write down that our function is x cubed plus 1. So if I ask you to find the derivative, right now you know that the limit of the difference quotient means derivative. So what I would expect to see is that you have f prime of x equals the limit. I am fine if you want to use h's. Raise your hand if you used h's in the last chapter. Okay. Then since a majority of us feel more comfortable with that, I'm going to go ahead and use h's up here. H is just in place of delta x. Okay? So the limit as the change in x approaches 0, f of x plus the change of x means you're plugging x plus h into your function. And then please do not forget that you need to subtract the function in its entirety. So you would want to put it in parentheses all over change in x. Okay. Now, I didn't put any of these problems on our Unit 1 test for a reason, because we're doing it here again today, and on your Unit 2 test there will be one. Okay, that's why you didn't see it on your test yesterday. So now we got to do some algebra, right? Because if we plug in 0 for h, we get 0 over 0. So we got to do some algebra. If we take x plus h, the quantity cubed, x cubed plus 3x squared h plus 3xh squared plus 1. If you need to multiply that out individually, that's fine. I'm remembering the Pascal's triangle and how it affects, and with the binomial theorem, how it affects our binomials to a power. Okay. And then we're subtracting x cubed plus 1. Okay, so what happens? X cubes go away. 1 minus 1 goes away. The h in the denominator is always a problem, so we need to look for something in the numerator, right? Do we have an h in common in the numerator? Okay.
Miss Holman,
Yeah.
shouldn't there be an h cubed on top?
Oh no, there should be. I put plus 1 instead of h cubed, didn't I? Or I just skipped over. Thank you. Plus h cubed plus 1 minus x squared. Thank you. What? Okay. We all make mistakes. Just gotta go back and fix them. Okay, so do you feel better about this? We agree with what's happening here? Okay. Now I need to evaluate the limit as h approaches 0. So I'm plugging 0 anywhere there is an h. I no longer need to write the limit because we have now evaluated it. We get our limit to be 3x squared. So we describe our derivative to be 3x squared. Okay. Now, what does that mean? So first of all, I want you to be aware that when you do the limit definition of a derivative, more than likely, you're going to get an expression that involves x. Okay, it's going to be some sort of an equation. Okay. Let's think about the graph of our original function. Okay. X cubed plus 1. What does that look like? The cubic function, right? Shifted up 1. So we found that our derivative is 3x squared. Okay? Since that is our derivative, that is describing the instantaneous rate of change for x cubed plus 1, that is describing the slope of a tangent line at any point on x cubed plus 1. So let's say I were to plug in 0. What do I get when I plug in 0? We get 0, right? Oh, darn it. 3x squared when I plug in 0 is 0. That's because we have a slope of 0 at 0. It kind of flattens out and then it goes again. Right? What about this? F prime is what I'm saying. That means derivative. F prime of 1. When we plug 1 into 3x squared, what do we get? We get 3. Okay? At 1, we have a slope of 3 for our tangent line. What about f prime of negative 2? What would that be? What? 12. At negative 2, we have a slope of 12. It's describing all of the tangent line slopes for any point. And we can plug in an x value to figure out what the exact slope is at that point, but it changes at each coordinate. Okay? What's the only graph that would have the same slope everywhere? A line. Okay? If we have a line, we have a constant slope. Any other type of graph, the slope is going to change. Okay? Which makes it not a line. All right, so our derivative is going to give us different values at different points because that slope continues to change. Tomorrow we'll do more with working with the graphs and how they relate to each other. Okay. Now there's a concept that we need to talk about, and it's a mouthful. It's called differentiability. Right? Like, let's say differentiability. Turn to your neighbors and just have a discussion about what you think we're going to talk about with the word differentiability. Differentiability. How the one shows. So the derivative of a line would be a number, and it would be, so if the derivative describes all the slopes, and the slope of the line is always the same, then the derivative would be just whatever that slope is. So if we have the line y equals 2x plus 1, the derivative would be 2, because all the slopes are 2. Okay. All right, thoughts? High five. What'd you say?
The change in something, I'm not sure.
Okay. Okay, we're talking about the change in something. Part A.
I said it would compare the slopes of the like slopes of the different tangent lines of possible function.
Okay. Okay. Part 4.
That's kind of what we said.
Okay, just kind of compare the slopes. Okay. Would there ever be a time where we couldn't find a slope? Okay. Okay, so did you say like this? Okay, like horizontal slope would be 0, right? Okay, so vertical. Okay, that's what I was. Okay, so vertical, we would not be able to identify a slope. What about in a graph? Are there ever places where we don't have slope that wouldn't be like vertical? If we have like something missing, like discontinuities. Okay. So differentiability is basically talking about if we can take the derivative of a graph at that specific point, then we say it's differentiable. If we can't take the derivative, then it's non-differentiable. What? Really? Oh, and I didn't call on you. Okay, part 1, you had a good discussion. Okay, so we say we're differentiable if we can. We don't have to compare. Okay, good news, we don't have to compare. We just have to determine can we. Okay, I know, was it like pod 4, pod 8, I think pod 6 back there, you guys kind of had all that discussion about like comparing our derivatives. Just can we or can we not? If we can find a derivative, it's differentiable. If we can't find a derivative, it's not differentiable. Okay? So there's 3 cases that we cannot find the derivative at. Okay? I already kind of led you on a discussion on some of them. Pod 7, you came up with like vertical. Vertical tangents have no slope, right? Okay? Then we talked about maybe a hole. What else would be kind of grouped in that? Asymptotes, and what do we call those? Discontinuities. Okay, if we have discontinuities, those aren't good. Okay. There's one more case that you probably want to think of. Okay. So we have discontinuity, vertical tangents, and corners. Okay. Draw these 3 pictures for me, and then I'll talk about why a corner would be non-differentiable. So maybe start talking in your pods, why would a corner be a place that we couldn't identify a derivative for? And what are the issues there? Or if you think that we could, talk about what it would be. All right, part one. What do you have to say? Okay, we could draw a number of different tangent lines that look like they would be legitimate, right? Well, we can only have one tangent line, but we have like so many options here at that corner, right? So there's not like a straightforward way of drawing a tangent line at a corner. Okay. I want to talk about some specific examples with these. You don't need to write these down. As long as you have these three pictures in your notes, you'll be fine. Okay? But we do need to be on the lookout for things like this. Okay? This corner thing especially. Sometimes you'll hear it called a cusp. I call it a corner. I think Mr. Grable likes to call it a cusp. But they mean the same thing. That's something that we're really going to have to keep our eyes out for. Okay? So let's talk about that first. What graph can you think of that has a corner?
Absolute.
An absolute value. Okay? So the absolute value of x is not differentiable at x. We can find derivatives to the right of x, or 0, excuse me. We can find derivatives to the left of 0, but we cannot find the derivative at 0. Okay? Fun fact. You don't need to write this down. But the derivative of the absolute value of x is the absolute value of x over x. Look familiar? Right? And we know that that graph looks like this. We don't have a value at 0 because it's not differentiable there. There's a corner. Okay. Let's think about a vertical tangent. A graph that has a vertical tangent.
Like the line x equals 3. Just like that vertical line.
Oh, okay, like a vertical line. Yes, yes.
Oh, yeah.
That would be a good one. What about a graph that maybe is differentiable in other places but has a place of vertical tangency?
Ones where like the slope goes like down to negative infinity, like on the asymptote.
Well, we would still be able to. Never would it be vertical. Never would it be vertical because we're approaching those. But that's a good idea. And I think you guys are thinking of the same thing. Like we're approaching like the asymptotes. Okay. Those would never get completely vertical. Okay, because I mean they get pretty steep, but they never get completely vertical. A tangent graph would be a good example for points of discontinuity because we have all those asymptotes. Okay? I heard somebody whisper it, but I don't know if they're going to be brave enough to say it. What?
The cubic function.
Not the cubic. Cube root.
Oh.
Okay? Cubic function has a 0, like a horizontal tangency place. Its inverse, cube root, would have a vertical tangent place. All right, 2 more things to talk about. Okay. should put a screen shade. Okay. If f is differentiable, then automatically we know that it's continuous. If f is differentiable, automatically we know that it is continuous. Why? Okay, we don't have like an asymptote, we don't have a hole. And what did we say about asymptotes and holes? Can we find the derivative there? No, we can't. So if it's differentiable, automatically there's no points of discontinuity. Otherwise, we wouldn't be able to take the derivative. Okay? What about the converse? If it's continuous, does that mean it's differentiable? Eli, you're shaking your head right away. Give me an example.
The absolute value.
Okay, the absolute value. Is it continuous? Yeah, but it's not differentiable. So continuity doesn't necessarily tell us about differentiability, but differentiability tells us about continuity. Okay, I feel like I'm saying a lot of syllables at once. Right? But are you able to follow me here? Continuous does not mean differentiable, but differentiable definitely means continuous. Okay, the last thing that I want to make sure we talk about is some notation. Okay, so f prime of x, I've shown you. If your equation is written as like y equals, you may see y prime written. Okay, I know I'm covering some because I'm focusing on these right here. Okay. So f prime of x, you've seen that. Y prime is another one you'll see. Okay. If your equation is written as y equals blah, 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 y prime would be a good one to use. This notation right here means take the derivative with respect to x of, okay, so and then dy over dx, that's a very popular one. Okay. dy over dx, that's kind of describing like change in y over change in x, which is slope, right? So this is the calculus way of writing slope when we're talking about derivatives. Okay. This I would not worry too much about until we get to next week. But these other three, you're going to see me write interchangeably. Okay. dy dx, y prime, f prime of x. Okay. Now, we'll eventually start getting into like using different variables. And if we have an equation with t instead of x, then we'd be talking about like dy dt, because that's our variable. Okay. It doesn't always have to be dy dx. We might have something written differently, but we won't worry about that yet. Okay. So here's the deal. I think that's where I'm going to stop. I think I could have time to show you a tangent line equation, but I think we'll be okay. So in your homework, you guys have practiced the limit of a difference quotient before. So you know that the algebra may be a little bit intensive. Take your time, okay? Check your answers in the back of the book. That doesn't necessarily mean your work is going to match what it should be. But make sure you do check your answers and just have some patience, okay? It's gonna be algebra heavy. But it looks like you have 1, 2, 3, 4, 5, 6, 7 required problems with like 6 problems where you're saying if it's differentiable or not. Okay? So it's really not a long assignment.
Can you
Yes.
go back to focus on
Like 1, 2.
Oh wait, no, right
This one?
Yeah.
Okay. And everyone has a gold sheet. Okay, we have 4 minutes left in class, so I'm going to introduce you to a game.